consider the set of functions s equal to x squared minus 1, x squared plus x, x plus 1. These are all solutions to the differential equation y triple prime equals 0. First, is the set S linearly independent? If not, then find a relation. Now, what do we mean by linearly independent? The idea is we take our functions, we take all linear combinations. So we'll have A, B, and C. These are numbers. And then multiply each function by one of those, sum. Set that term equal to 0. Then we look for all solutions. So I'm looking for A, B, and C that make this equal to 0. We always have the solution A equals B equals C equals 0. So we're interested in the others. If there are no others, then we call our set linearly independent. If not, linearly dependent. Now, what does linear independent really mean? The idea is, if I consider all linear combinations here, linearly independent says if I throw away any one of my functions, then the set of all linear combinations is going to get smaller. So in some sense, a linearly independent set requires every function that's in there. If you throw anything away, you get a smaller set. If I'm linearly dependent, what happens is you can write one of the functions in terms of the rest, which means if I'm taking linear combinations, well, that function I can write in terms of the rest is a redundant one, okay? We're not going to get anything new using that function. So the idea is I can throw away that function, then the set of linear combinations won't get any smaller. I can throw that function away, space of linear combination stays exactly the same. For linear independence, we use the following theorem. Okay, our set S is linearly independent if and only if the Wronskian is non-zero at all points in the domain. For the Wronskian, we define this as follows. Take our set, okay, we have our set of functions, load our functions into the first row of a matrix, first derivatives into the second row, second derivatives into the third row. Then I take the determinant. Okay, in our special case, x squared minus 1, x squared plus x, x plus 1, the derivatives, and then the second derivatives. Then we only need to take the determinant. Okay, in this case, we have a 3 by 3 matrix, so we get the determinant by just multiplying down diagonals. Okay, if I write this matrix out next to itself, off to the right, I'll take the first 3 diagonals, multiply down, going to the right. Then we'll take the diagonals going down to the left, multiply down, and subtract. So what do we get? Okay, first diagonal I multiply down, we hit a 0, so I get a 0. Next diagonal, I have 2, 1, x squared plus x, so we have 2x squared plus 2x. Third diagonal, x squared plus 1, 2x, 2, gives me 4x squared plus 4x. Then we go in the other direction. So if I start with x squared minus 1, I'll hit a 1 and a 2. So that gives me minus 2x squared minus a minus 2. So that gives you minus 2x squared plus 2. Then what do we have? For x squared plus x, we have a 2x and a 0. So that goes away. And then we're left with the 3 terms on this diagonal, which gives me a minus 4x squared plus 6x plus 2. When we collect powers of x, what happens? We get 0 plus 0 plus 0 gives me exactly 0. So this is 0 for all x. That means our set's linearly dependent, which means there's going to be a relation. Now, our set is small enough here that you can get your relation just by eyeballing the set. Note, what do we have? If I want to get x plus 1, I can get that by taking the x squared plus x. Okay, that has plain old x in it. Subtract off x squared minus 1. So you get your relation by setting a, b, and c equal to a equals minus 1, b equals 1, c equals minus 1. So that gives us the relation. Then note, to get the span of our set, okay, consider all the linear combinations. You actually only need, say, the first 2 to get all linear combinations. Then, okay, we have a third order linear differential equation with constant coefficients. So we know that we need at least 3 functions to get all solutions. So you can play around with that, but what you should do is take the function, okay, equal to 1 exactly. Okay, that's definitely a solution to y triple prime equals 0. Check the Wronskian with that function replacing x plus 1 and see if you get something that's not 0.